Well, it's my pleasure to hand over to a friend of mine from Australia, Dr. Luke Barnes. He is Senior Lecturer in Astronomy and Cosmology at Western Sydney University. He did his PhD at Cambridge University in the UK, and he focuses on the cosmic evolution of matter. How is that even a thing? How does matter evolve? Maybe we can ask him that later. He's published widely in galaxy formation and fine-tuning, which is his topic really tonight. He's the author or co-author of A Fortunate Universe, which is a best-selling book, which he wrote with his atheist scientific colleague. His most recent book is, let me get this right, The Cosmic Revolutionaries Handbook, published by Cambridge University Press. And in my Undeceptions podcast, Luke is basically the phone-a-friend on all things sciencey. So it's great to be able to introduce him to you here at Wheaton. Will you welcome Dr. Luke Barnes?
All right, 1 second. Well, thanks for coming out. Thanks for moving forward. The alternative was me delivering this from the fourth row, so thanks for that. I'm happy to do it from the fourth row if that's what you're after. Thanks very much to John. So if you cast your mind back to those dreadful years, about 4 years ago, 4 and a bit years ago, when things were starting to be cancelled, I had the distinct ignominy of being John's first COVID cancellation. I was organising an event which brought John out to the Penrith Observatory to talk about various important things, and then suddenly tickets stopped selling for some reason. So sorry, John. But it's great to be here, great to be talking to you, great to be talking about this particular question. Was the cosmos expecting us? Which seems a very strange thing to ask, perhaps, especially if you're a scientist. Expecting, that's not the sort of thing scientists might talk about. Cosmos surely don't expect anything. And yet, this topic, which I'm going to talk about tonight, the fine-tuning of the universe for life, is one that I've seen grab a hold of a whole bunch of very different audiences in very different ways. When I was a researcher at the University of Sydney, I'd completed a review paper about the scientific work in this area and was asked by my colleagues at the Sydney Institute for Astronomy there to give a talk about it. Now, for those who don't know, the way an astronomy seminar usually goes is as follows. You have about 50 minutes. You'll spend about 45 minutes giving the talk, leave 5 minutes for questions, and then everyone goes to lunch, right? So not too many questions, okay? Because lunch is coming. I thought, you know what? I bet there's going to be a lot of questions. I'll finish a bit early. I'll leave 10 minutes for questions, just in case. We were all there an hour and a half later. No one left, because no one could leave this thing alone, right? And not only were people asking questions, people were answering questions, which is very unusual. So I also, a couple of years after that, gave a talk to a group in New Zealand called Skeptics in the Pub, where the details very much all in the name there. There was a pub, they were skeptics, and I gave a talk. To their credit, they invited a Christian to give a talk there. But what was interesting was I gave my usual talk about this particular topic, and then the questions started coming. And then the questions started to be intercepted indeed, before they reached the front. Not only was the audience asking questions, but they were interrupting me to answer the questions asked by the other skeptics. No one could agree in that room what they should do with this particular fact about the universe. It was one of the most delightful experiences of my life as a group of skeptics started arguing with each other. I hope it happens to you one day. Even on this trip, I've come from the University of Florida, where I gave a seminar, but not to the astronomers, to the philosophers. Right? A secular philosophy group run by a guy who was very clear to me that he was an atheist, but still wanted me there to give a talk about this particular topic. to all the undergrads they could round up and anyone else who wanted to turn up, especially all the philosophy students, and co-sponsored by the School of Religion and all sorts of other things. This is a topic that grabs people in a very interesting way, that people can't really sort of leave it alone. This has to mean something, or they have to explain to you why it definitely doesn't mean anything. But whatever it is, something has to be said. So what is this topic? As an astronomer, my job is, well, one of the wonderful things about it is I get to study the universe. The universe looks like this. This is a massive advantage of what we do. When we gather around in our sort of weekly meetings to discuss what's the latest in the world of astronomy, a part of that will be, let's just look at the most recent pretty pictures about the universe. This is one of the highlights of my job. You can do this as well. Just get yourself a really nice screen, get yourself along to the Hubble telescope website, put on some Beethoven, you know, just really make an evening of it. My job as a theoretical astrophysicist is to try not just to enjoy this, which I definitely do, but to try to understand it. Like, what's going on here? Why does it look like that? What are the physical forces that are shaping the universe we see around us? So what I see here primarily is a number of things. I see gravity drawing things together, but I see sort of the effects of rotation forming the matter there into a disk. There's all sorts of other interesting things going on here. There's also evidence of cosmic explosions. This is a supernova remnant. This is what happens when a star blows up. There's also, yeah, can we kill the lights for it? Is that possible? This is way prettier than me. No, not out there. They're fine. It's these ones. Welcome back. Okay, don't kill the audience lights, they might leave. Okay. Look, get a nice screen. Beethoven. All right. These are another famously beautiful bit of the universe. What I see here is what was once a cloud is being eroded by light coming from the top right. These are the densest bits left as light is sweeping from top right to bottom left, sort of eroding the least dense bits and leaving the most dense clumps behind. So what I want to do, what I try to do, is to understand the way the universe works in terms of the rules behind the scenes. So the way that physics in general, astrophysics in particular, tries to explain the universe is in terms of three things. First of all, there are laws, things like gravity. Right? It's no coincidence you're all sitting on the floor and no one is sitting on the ceiling. That's gravity. There are pushes and pulls, there are interactions, there are rules about the way the universe works. But there's not only that. So, for example, if you want to know where Mars will be tomorrow night, you need to know the law of gravity. But that's not enough. I can't just give you Newton's equation and you go, oh yeah, Mars will be over there. That's not good enough. You have to know something else, which is an initial condition. For example, where is Mars tonight? You could take that information and with the law of gravity, work out where Mars will be tomorrow night. But there's a third thing there in those laws. If you remember your high school physics, or if you'd at least like to sort of humour me and pretend you remember your high school physics, there's a number in there, big capital G. Newton's gravitational constant. It's just a number. The important thing about that number is, ordinarily in physics, what we want is for numbers to come out of our equations, out of our models, because that's the predictions. That's where you work out whether, it all made sense. So you want to put in, set up the problem, and then what comes out is where Mars is going to be tomorrow night. These fundamental constants are numbers you've got to put into the equations. The equation doesn't tell you what it is, you've got to tell the equation. You've actually got to go out and measure this thing. Why do these constants matter? Because they're what we're going to be focusing on here. Well, they matter because they set a number of extraordinarily important properties of the universe and of the things the universe is made out of. So, for example, let's go to sort of the bottom level, the smallest stuff we know about in the universe. If you took any of the matter you see around you and broke it up into the smallest pieces that you could. You might be a particle physicist, if that sounds enticing to you. And the smallest pieces are known as the up quark, the down quark, and the electron. There will be an exam later. The up quark, the down quark, and the electron. Now, they have a small number of properties. They're actually quite simple things in terms of specifying exactly what they are. For example, one of those properties is simply their mass. How heavy are they? And there's a very small number. We know what that number is for all of these, small in any sort of reasonable sized units. But there they are. Those are the smallest pieces. Those are the Lego building blocks of the universe. What happens next? What can I build out of these? Well, let's imagine, if you like, as I go that way, a production line of a factory. Suppose I give you, as many quarks as you can eat. All the up and down quarks and electrons you could ever want. What can you make out of them? Our universe is made of the right stuff that you've actually got a lot of options. You can build up a lot of structure. Yes, there's only 3 types of brick in your Lego set, but there's an awful lot you can make out of it. Let me just quickly go through this. First of all, starting from the sort of raw ingredients in the production line, the first step is that you can make protons and neutrons, which you've hopefully heard of. Those are the next step up. What's next is those protons and neutrons you can turn into the nuclei of atoms, right? Just hands the protons over here to this person who starts making nuclei of atoms. The protons and neutrons will stick to each other. And the electrons will stick to both of them, but not as closely. They'll sort of go around the outside. But our universe, there's not just one recipe for this, which is crucially important. You can decide, if you like, how many protons you want to stick into the nucleus. And all of the available options for that are precisely the available options of the periodic table. Here's atoms. Right? Quarks, protons and neutrons, nuclei, atoms. There's 92 naturally occurring atoms, the first 92 elements of the periodic table. I've made that too small in case it brings back memories of high school for anyone. But there's the options of atoms. And atoms can make molecules. The way that works is if you put atoms close enough, the electrons just won't go around their own home atoms. They'll go on a complicated path around all of them, and they'll bind the whole thing together in a chemical bond. It's a 2-sentence summary of chemistry. It's not that hard. Put enough of these chemical bonds together, bring enough nuclei together, and you can start writing code. You can write the code for stuff. This is DNA. Can I remember what the elements are? No, I can't. I've got to read them off the slide. Hydrogen, oxygen, nitrogen, carbon, and phosphorus. In that order, you can write the instructions for a person in a way that is unbelievably wonderful, and you should go learn more about that. Specifically, going to our next step, once you've got the code for this stuff, you can then actually start putting some things together thanks to proteins. Right? The proteins that are coded in DNA go in to make things like cells, and now I'm like way outside of my field of expertise. Right? We left astrophysics a while ago. But the cell is beautifully complex. That's another thing you should go and look into. It has its own postal system. It's just fantastic. And if you put enough of those together, you can make some small people, I'm told. Right? So, that's where we arrive at. There's this chain, this hierarchy. You can start with the basic stuff and build up and build up and build up in complexity and sophistication. You can encode information. You can have all sorts of wonderful things and eventually arrive at something capable of, enjoying a trip to Switzerland. So, the reason why these constants matter is they're right back at the start. The masses of those electrons, the masses of the quark, the up and the down quark. They matter to this whole thing. Because if you start messing with things back at the start of the production line, how much of that production line is still going to be there later on? All of this, perfectly normal physics questions. If you have any model in physics, any mathematical model, and you've got some free parameters in it, some numbers you've got to put in, it is perfectly normal and natural and expected, in fact, that you'll ask the question, what if those numbers had been different? What if I change them a bit? What happens? So, physics for the last couple of decades, asked itself, what if the constants of nature had been different? And I'm going to take you on a quick tour through a bunch of possible universes. So, let's get started. We've got 3 basic pieces of the universe. Electron. Let the record show everyone said that perfectly in unison. Up quark, down quark, electron. Look, it might win you a trivia quiz at some point in your life, so maybe put those away. Okay, we've got their masses, and it's just a number, right? In kilograms, it's some ridiculously small number, but it's just there, it's a number. If we're thinking about the possibilities, though, we've got 3 numbers, so I can represent the possibilities as a point in a 3-dimensional space. This way, that way. Which means if you want to order yourself a universe, you can imagine picking a place in this block. Think of a 3-dimensional block where every point represents a choice of those 3 numbers, a sort of continuous choice. If you want to know where we are, you can see yourself labelled there if you want to find yourself later on. That's where you are. Now, just for the nerds, if you're not mathematically minded, look away now. The axes here are logarithmic, which means they don't step up linearly, 1, 2, 3, 4, 5. They step up in powers of 10. 1, 10, 100, 1,000. Put an extra 0 on each time. This is a widely used thing, especially when you have to deal with, literally, for a living, astronomical numbers. There's a reason why it's cut off at the top. The reason is, if you were up there, you would have a particle so massive that it would become its own black hole. And at that point, physics goes, well, I have no idea what happens next. So we just don't know what happens up there. It's called the Planck mass. There's a similarly nerdy reason why the bottom is actually less exciting, but nerdy reason why the bottom is cut off. But in between those 2 limits, we have, as you can see, 60 orders of magnitude, 60 powers of 10. So pick a point, and you've ordered yourself a universe. Which universe would you like to order? Well, let me help you choose from the menu. I'm going to carve off bits of the menu that you probably don't want to order, for reasons I'll show. How? One thing that's important about all of this is at no point is mathematical consistency or anything like that going to help us out. Mathematically, everything's fine. We've got equations, they make predictions, off we go. That's all wonderful. It's on some other criteria that these other universes aren't the greatest. So, for example, I've carved off some pieces around the back there. Don't choose those universes. For the following reason, we can start our story again. Up quark, down quark, electron. Great work, everyone. Well done. What happens on the next step? Well, what happens on the next step is you don't make protons and neutrons. On one side, you actually make what's called the delta plus plus particle. Again, boring detail. 3 up quarks, or the other one's a delta minus, 3 down quarks. Here's the important thing amongst the names. Delta plus plus particles do not stick to each other. Delta minus particles do not stick to each other. So remember on the story where we ended up with people over there, the important thing that happened at this step was protons and neutrons stick together to make nuclei and then atoms, and then off we went. In those universes, this whole story ends here. We're done. That's it. That's all you can do. You could make a pile of these, but a pile is all you've got. You're not going to be able to code anything. You can just make a pile of stuff. That's it. In those universes, the possibility of complexity is cut off. You just can't make anything. In fact, with a smaller slice cut off there, you can make universes in which the following is true. You can make protons and neutrons. So here's a very simple picture of an atom. And points if you know which one this is. I think I heard it. Deuterium. Well done, go to the head of the class. With a very small change to the masses of the fundamental particles, you can make it the case that, yeah, sure, the electron will go nicely around the outside. This is where most of the special effects budget went, so just enjoy this. That'll all happen very nicely, but that proton and neutron, they won't actually stick to each other. And so, actually, again, the story will end here. Quarks, proton and neutron, but no nuclei. We can't make the next step because it won't stick. The reason for this is kind of interesting. You might think if you just change the masses of these fundamental pieces, you'll just make everything in the universe a bit heavier or a bit lighter. But what actually happens is that because energy is the sort of currency of the universe, if you want something to happen, you've got to be able to pay for it with energy. And because of what I promise is the only equation in this thing, E equals mc squared, mass is a form of energy. So if you start messing with the masses of these fundamental pieces, you change the budget of the universe. You change the things that the universe can and can't afford. If you want something to be stable, as we would like nuclei to be, the way to do that is to make it, in energy terms, broke. Don't give it enough money, enough energy to fall apart, right? So to keep your teenager out of trouble, just make sure they're broke, okay? It's not working for me, but never mind. That's the way that you can make this work. In fact, there's other changes we can make which form other sorts of disasters. You can make it so the electron doesn't actually go around, it will naturally spiral into the nucleus, turn all the protons into neutrons. That's a real interesting universe. By interesting, I mean sort of for a physicist, there's no one there. Here's the periodic table again, just for fun. This is the astronomer's periodic table. It's coloured according to where that element is made in the universe. So you can see ones left over from the Big Bang, large stars, supernovae, cosmic rays, small stars, and the ones that we decided to make for some particular reason. If you have a universe where you've just set the dials slightly wrong for the masses of the fundamental particles, in the ways that I've been describing, the periodic table looks like this. At this point, the chemistry students usually start cheering, but I'll leave that up to you. The reason, so, for example, in this universe, the chemistry exam goes like this. Question 1, what is the element? Hydrogen, thank you. Question 2, what is the chemical reaction? Because there's only one. You can make that. In other words, 1 + 1 = 2. You can put two hydrogen atoms together, make a hydrogen molecule. That's the end of the chemistry test, because there are no other chemistry facts, because that's it. That's all that happens in chemistry. Sadly, there's no one around to take that exam. Once you've, as physicists, as we've looked at these sorts of catastrophes in failing to walk the path of complexity, once you've worked out all of these and started to carve off various regions in the menu, from that entire block, the bit that's left turns out to be this thin slice. You've got to land there. On perfectly objective grounds, if you coloured in, where in this slab, how many of the elements in the periodic table will be stable and actually produced in the universe? And for the vast majority of the slab, the answer is either 1 or none. Except for this beautiful slice where we are, where the answer is suddenly 92, and you can make people. Incidentally, now it's relevant that I sort of distorted the axes a bit so that you could see what's going on here, the logarithmic axes. If I hadn't done this, if I hadn't done that, you would need a screen 3 light years tall in order to actually see that region. So hence why I distorted the axes there for you. This is an extraordinarily small sliver of the possibilities. This is the picture you can have in your head of the fine-tuning of the universe for life. Just so I can do my job, theoretical physics, we can explore ways that the universe would have been if these numbers had been different, these fundamental constants. What if? And the answer was rather surprising. There's something pretty rare going on around here. These aren't just any old atoms you're made out of. Let me give you a few other ways to ruin the universe just before we move on. Stars. There's our sun. Stars are actually remarkably easy to model. They're remarkably beautifully simple things. At their most fundamental, they're a balance between, on the one hand, gravity, trying to pull everything towards the centre, and heat, or pressure, gas pressure, which is the property, you fill a balloon with air and it doesn't like to be squashed. Just that, right? Gases push back. Those two things in balance provide the stability of stars. In particular, if a star for any reason expanded a little bit, gravity would pull it back to where it started. If it contracted a little bit, heat would push it back to where it started. Right? Stars are remarkably stable. However, if we change the strength of gravity, if we turned it up a little bit, on a remarkably small amount compared to the sort of range it could have had, it turns out it's quite easy to make stars which don't have that property. The balance between the forces has to be absolutely perfect, because as soon as you step away from that, the star starts to overreact. If for any reason the star contracted a little bit, yes, heat would push back, but it would push back too much. The star would overreact and those oscillations would grow. You get stars that start to pulse. And eventually, one of the particularly big pulses will simply blow it apart. We see very, very big stars in our universe doing exactly this. Change the numbers of nature just a little bit, and every star does this. And you have a universe where anything big enough to burn is big enough to blow itself apart. Finally, looking at the very largest scale, and now I'm going to ask you to kill the lights again. Thank you. Excellent. This is a simulation of how we think galaxies form, done by a collaboration of people known as the Eagle collaboration. I'm going to ignore that, we can all ignore that. We're going to teach a supercomputer how to solve the equations of physics, and we're going to start with a universe that's almost perfectly smooth, and then watch as gravity pulls matter together within an expanding background. What you can see here is that anything that's anywhere in the universe that's dense, because it has more matter there, it will pull more strongly on everything around it. So, in a sense, the rich get richer. The dense bits of the universe get denser, and structure grows. From an almost perfectly smooth universe, we get one where there are dense knots, where you will find galaxies and clusters of galaxies. They've got their matter at the expense of these voids you can see, and in between them, this whole thing is called the cosmic web for hopefully obvious reasons. There are these filaments where the matter hasn't quite decided which way it wants to fall. But at the end of all of that, we have a picture of the universe which does a pretty good job of resembling the actual universe. The universe we see has this sort of hierarchical structure. This is the way that our universe turns simple initial conditions, an almost smooth beginning of the universe, into interesting final conditions. It's the equivalent of the production line, but starting off with almost perfectly smooth beginning, down to, at this end, galaxies, stars, planets, and the things that live thereon. It should not be underestimated how difficult that job is. The air in this room is a billion times more dense than the average density of the universe. Say that again. The air in this room is a billion, 10 to the 27, times more dense than the average density of the universe. If you take your favourite cubic foot of space, in this room, you've grabbed a certain mass, right? There's a certain mass of air in this amount of space. Go out into a typical bit of the universe, pick somewhere at random, and grab the same amount of space. How much matter will be in there? A billion times less than there is in the air in this room. In other words, in order for a perfectly smooth, where everywhere is average, universe to turn into a universe where there's things like the air in this room, the universe has a lot of work to do in bringing a lot of stuff together from all over the place to assemble the stuff we are breathing right now. What happens if you start messing around with the numbers behind the universe? This seems, when I say it out loud, it seems megalomaniac, sort of, like a megalomaniac of some sorts, right? This is a great, how do I say this? If you're thinking of being a supervillain, I've got some great ideas. This simulation was done by a number of researchers, including a group at the University of Durham. Working with them and a number of other colleagues, including Geraint Lewis, my co-author, we used the same code that was used to make this particular simulation, the Eagle simulation, and we changed the numbers. In particular, we changed a number called the cosmological constant. The cosmological constant is a very sort of infamous number in cosmology. It represents the fact that the expansion of our universe is accelerating. So if you look at a typical galaxy out there, right, so there's one over there, we've known for the last 100 years it's moving away from us. That's the redshift. Since 1998, we've known that it's moving faster today than it was yesterday, which is a pretty weird thing, actually, because that's not the sort of effect you would get from just ordinary gravity and the stuff around us. The number that we use to describe the magnitude of that effect is the cosmological constant. We don't know why it is what it is. It's one of these fundamental constants. You just put that number in and suddenly your model starts explaining a whole bunch of stuff. So what if it was different? When I hit play, nothing's happening yet. When I hit play on this, the left panel is roughly going to be our universe. You'll see the whole production line beautifully heading towards structure on every scale in the universe. In the middle and on the right will be what happens if you change this number, this dial. Now, relative to the entire scale that it could have had, these changes are rather small, but relative to the value in our universe, they seem larger. It's 10 times larger in the middle and 100 times larger on the right. So as I hit play, they start off almost the same because it takes a while for this effect to happen. On the left, as you can see, structure is forming. We're moving along the production line. On the right, the acceleration of the expansion of space is moving everything really far away from everything else. And so that process of gravity holding on to grabbing a hold of things and forming more and more structure gets cut off. The production line simply shuts down. Excellent. Let me go back for another quick look at that. For the following important reason. This took ages. Sorry, this was part of my research for an awfully long period of time. And yeah, did this take a lot of work? So we're all just going to appreciate how much. I mean, all the other slides took like, what, 5 minutes a minute? This is like, yeah, thank you. All right. This is the fine-tuning of the universe for life. Of all the possible values of the fundamental constants of nature, the subset that permits the existence of life seems very small. There's these dials. We don't know why they have the values they do, and so doing what all physicists do, we spun them a bit. And mathematically, everything was great. And in terms of the production line to complexity, things got real bad real fast. So, this is the book, the cover of the book that I wrote with Geraint Lewis, A Fortunate Universe. As was mentioned previously, Geraint's an atheist and a Welshman. One of those things is shocking. An unbelievably proud Welshman, by the way. It's hilarious. Anyway, he'll explain to you in great detail the connection between Wales and Elvis Presley, which no one else believes, but he's quite adamant. This is a book that has 8 chapters, and 7 of them we wrote together. And apart from one footnote that you can go and find in your own time, we agree on all the science. In a week, I'll be on a plane to Durham in England, actually, where I'll look into the people who did the Eagle simulation. But I'm actually there for a conference in which Geraint and I are speaking. And we'll basically do the first half of this talk, but as a double act. Right? He could have given this up until now. He has. We've done it before. I'm doing the slides. We agree about the science. Just an aside, the weird thing is the conference is about panpsychism and pantheism, and neither of us are either of those things, so why we're there is another question entirely, but they wanted to hear about fine-tuning and we went, well, I'll go to Durham, that's fine with me. This is the fact that you present it to a whole bunch of different rooms and no one can leave it alone. My favourite summary of reactions to the fine-tuning of the universe for life comes, I think this is a quote from Alistair McGrath, but I haven't been able to find the original. I just want to give him credit because it's really funny. I'm not religious, but something weird is going on here. That's a pretty good summary of what's going on. Let me try to make that a bit more precise. What can you make out of this? What can we do with, I mean, it's weird, but what can be made from this? At one level, the fine-tuning argument is a design argument. And on one level, does design need an argument? I mean, maybe we should all just sit here and stare at the screen for a while, and if that doesn't look like design to you, then I can't really help you. I mean, if you can't see it in there, are you going to see it in some equations? I've been using this illustration for a while. I think my phone heard me, because shortly after this, Facebook started trying to sell me this. And I haven't bought one, but I really want to. I mean, so I've been reading I've been reading William Paley again. Paley famously presented the design argument at the start of the 1800s. And his argument takes the form of, an analogy. If you found a watch, you wouldn't just assign it to the laws of nature, you'd say someone designed the watch. And yes, it's an analogy. But as Paley continues to just absolutely pound it home chapter after chapter, you've got to think this is the best analogy you've ever seen in your life. If you can't follow this analogy, then no analogies are good analogies. I mean, if that looks designed, why on earth wouldn't the real thing be designed? And the answer to that for a lot of people, especially modern people, seems to be, well, science has explained the natural one. We have an explanation for the natural thing. So here is Richard Dawkins. Biology is the study of complicated things that give the appearance of having been designed for a purpose. Physics is the study of simple things that do not tempt us to invoke design. In other words, he's freely admitting that essentially biology is lost in terms of, is there design out there? But as long as he can find a process that sort of reduces biological processes down to physical and chemical ones, then thank goodness we won't be tempted to invoke design down there. So what the rest of the book, this is chapter 1 of The Blind Watchmaker. If he was serious about this, the rest of the book would be about physics, right? Because that's where we now have to look. Now, I don't want to start a turf war, but actually, sorry, I said that wrong. I do want to start a turf war. What does physics say about this? The important point he's making here, and the thing to recognise is that the problem has not been solved, it's been moved, as far as Dawkins is arguing, even on his own terms. Is there design in biology? Well, as long as you grant a number of other things, as long as it doesn't look like there's design in physics, then everything will be all right. So to turn that another way around, what Dawkins is asking is, are the fundamental physical processes that shaped our world boring and unexceptional and unremarkable and typical? They're just any old atoms, any old universe, just expanding in any old way. What's great about Dawkins is whatever he's saying, he says it beautifully, clearly. Wonderful writer, of course. But there's a method in chapter 1, if you read it carefully. Here's a long quote. Let me take you through it. It is true, says Dawkins, that there are quite a number of ways of making a living, flying, swimming, swinging through the trees and so on. But however many ways there may be of being alive, it is certain that there are vastly more ways of being dead, or rather not alive. You may throw cells together at random, over and over again for 1 billion years, and not once will you get a conglomeration that flies or swims or burrows or runs or does anything even badly that could remotely be construed as working to keep itself alive. In other words, says Dawkins, why is it the case that there is the appearance of design in biology? One of the ways that we could diagnose that intuition is to say, what would happen if you took a typical living thing and sort of threw its cells together at random? And, says Dawkins, perfectly obviously, it wouldn't fly. The hummingbird, as well as needing amazing cells, needs them in a very particular order in order to fly. But there's a method there, right? What happens if you throw the bits together at random? So if he was really serious about the question of are we tempted to invoke design at the level of physics, he would ask the question, what happens, not just if you throw cells together at random, but what happens if you throw a universe together at random? And the fine-tuning of the universe for life gives us a way of thinking about that. Rather than just imagining a whole bunch of other universes, we can take these numbers, and there's a certain number of them, 31 if you're playing along at home, and they vary over certain ranges, and if we do our job as physicists, we can work out what would happen in any particular set, for any particular set of constants, and so we can work out what would happen if you throw a universe together at random. And that's the question answered by fine-tuning. The answer is it doesn't fly. Doesn't do any of this stuff, doesn't get anywhere down the production line, doesn't make any sort of complexity at all, on very general grounds. We're not talking about, if you get the electron mass wrong, then the froth in my latte won't come out right. We're talking about whether things stick together at all. Can you make any sort of complexity? There are 3 basic elements. What can you make out of that? If the answer is a pile and nothing else, you're not going to get life or anything like it in that universe. If you get the cosmological constant wrong, no 2 particles are ever going to touch each other in the history of the universe. That's the sort of disasters waiting here. That's what happens when you throw a universe together at random. But if that's right, then the exact same intuition is still there at the bottom level. It didn't leave. Physics does tempt us to invoke design. And now Dawkins has a real problem. There's nowhere else to go unless you manufacture it yourself. The multiverse. It should be a bit of a clue that otherwise sober scientists have, at this point, an awful lot in common with, Spider-Man. But it's an idea worth thinking through. Did we get lucky? Maybe the universe, is one of many, and like a winning lottery ticket, it's just sort of handed its useful properties by all the other losing tickets that everyone else bought. Perhaps these constants vary through space and time, creating a vast number of other universes. It's worth thinking through. Cracks about Spider-Man notwithstanding. But in terms of the question we're here to ask, here's the problem, the central problem I want to raise. If we're really interested in what do I do with my intuition that the world looks designed, Dawkins said, go look at physics. And we said, we did, that looks designed as well. And so actually in the God delusion, by the time he's got to there, he's like, well, what if there's a multiverse? But if you're very serious about that, you should be asking now the next layer down. What happens if you throw a multiverse together at random? And that is a question that no one has the slightest clue how to answer. There is no, in the middle level of physics, these numbers are part of an extraordinarily well-tested model of the universe. The standard model of particle physics, standard model of cosmology, do an awful lot of very good work in accounting for a wide range of observations of the universe on all sorts of scales. They have been very, very well studied. We don't have anything remotely close to a standard model of the multiverse. We have a couple of toy ideas that maybe sort of half work to illustrate some points about what might be there in a future theory of physics when it comes along. We don't even have our model, let alone lots of them that we can start thinking about multiverses thrown together at random. We're just not remotely there. So this tactic is really the sort of equivalent of not can we play a different game, but can I take my bat and ball and go home? It's that sort of move. What if I took this really important question and kicked it so far that no one knew what the answer was? Well, at that point, the thing to say is that all the science we have pointed in a certain way. And if you can imagine science that points another way, that's wonderful for you. But let's be clear about the direction that all the science we know, points. And that's in the direction of design. That's one of the things about this particular argument that I think is very arresting. First of all, that it started in the physics literature. Secondly, that it's been defended, the basics of the if I change this number, then this happens. That those calculations were done, not by philosophers, not by theologians, but by physicists just doing their job. That the major publications in this field were not, again, they didn't come out of theologians or philosophers, they were cosmologists, and particularly well-known cosmologists. People like Paul Davies, whose book you might be familiar with, John Barrow, who worked at Cambridge University. The famous paper on the fine-tuning of the cosmological constant was written in 1987 by Steven Weinberg, a Nobel Prize-winning astrophysicist and outspoken atheist. But he could do the calculation. He knows the way it works. In 1999, a very good book on fine-tuning, still worth reading, called Just Six Numbers by Martin Rees, or to give him his full title, Sir Lord Baron Rees of Ludlow, President of the Royal Society, Master of Trinity College, Astronomer Royal. A big deal. And also rather small, which is very off-putting when you meet him for the first time. Like, he's a giant, and he's... Anyway, that's another story. Wonderful person. This is why this gets attention. And in particular, at no point in the argument do you have to argue that some scientific theory is wrong. That's not what's happening here. The question is, how do we take stock of where we are with the best science we have today? Which way is it pointing? And it's pointing exactly the same way that the hummingbird is. So it should return you to that intuition. If you see in nature a designing hand at the level in front of you of a hummingbird, or whatever it is about the natural world that you find just flabbergastingly amazing, you should understand that that impression will follow you all the way to the bottom. That science will not overturn it at all. It will still be there. Let me finish with one of my favourite quotes. We should be astonished by nature's regularity, says Henri Poincaré. Men demand of their gods to prove their existence by miracles, but the eternal marvel is that there are not miracles without cease. The world is divine because it is a harmony. If it were ruled by caprice, what could prove to us that it was not ruled by chance? Thank you.